Hello, everyone. Thank you for coming. I really enjoyed this opportunity to share some information with you. I'm going to talk today about basis sets, and Alan here is going to talk about electronic structure theory. So first off, I want to tell you a little bit about this presentation. Many of you are here because you want to know what basis sets are. For example, what is a Popol split valence basis set? And also, you want to know what basis set to use and where in your electronic structure theory calculations. They're good. Most of the tips that I'm going to give you today are qualitative and intuitive. For example, should I use diffuse functions for anionic molecules? I'm going to tell you, yes, you should. However, the nomenclature is a little bit challenging, and basis sets have multiple layers, so you might need to do a little bit of self-studying on your own to really master the topic. So first off, what is a basis set? A basis set is just a collection of vectors which spans, in other words, defines a space in which a problem is solved. This basis set can be either orthogonal or non-orthogonal, meaning that the vectors are 90 degrees with respect to each other. So in 3 dimensions, we could choose x, y, and z as our basis vectors. And this is an orthogonal 3D basis set. In quantum chemistry, the basis sets usually refer to the one-particle functions used to build molecular orbitals. This is often referred to as linear combination of atomic orbitals, or LCAO theory. So LCAO theory is represented by this equation right here, which just says that the orbital is a combination of atomic orbitals. I like to think about this equation, though, as basically the orbitals are the little house for the electrons, and the basis sets are like the Lego pieces that we build the house with. There are many different choices for basis functions that we could choose. One particular choice are Slater type orbitals. Slater type orbitals are essentially just exponentially decaying functions. These Slater type orbitals are exact for the hydrogen atom. This R term out in front gives the orbital, the basis function radial nodes. Y here is the spherical harmonic and gives it angular nodes. And N, L, and M are the quantum numbers for the atom. Zeta here controls the width of the Slater type orbital. So a large zeta means that the Slater type orbital decays very fast. It's very tight. Whereas a small zeta means that the orbital decays very slowly, and it's called diffuse. However, Slater type orbitals are not suitable for fast calculations of necessary 2-electron integrals in electronic structure theory calculations, so they're not commonly used. Another choice for basis functions that we could choose are Gaussian type orbitals. Now, instead of the orbital decaying as r, it decays as r squared. The sum of the exponents at the Cartesian coordinates x, y, and z now controls the angular momentum. For example, if a, b, and c are all 0, then we get an s-type orbital, or basis function, I mean. If either a, b, or c is equal to 1, then we get a p-type Gaussian type orbital, and etc. So this graph over here just shows you how it decays as a function of nuclear distance. These are often called Gaussian primitives because technically we're not talking about orbitals here. We're talking about basis functions. So the nomenclature is just a little confusing here because these are the basis functions which build the orbitals. So the more modern terminology for these is Gaussian primitives. So what are the pros and cons of these Gaussian primitives? Well, these Gaussian primitives actually are very efficient for electronic structure theory calculations because the product of 2 Gaussian primitives is itself a Gaussian primitive. So this actually makes these very efficient for these electronic structure theory calculations. However, the Gaussian primitives don't look like the Slater type orbitals anymore. You could see that in 2 places. So near the nucleus, the Gaussian primitives don't have this. This is the Gaussian primitive. This is the Slater type orbital. The Gaussian primitives don't have a cusp, which is what we want. Furthermore, very far from the nucleus, the Gaussian primitives decay much faster than the Slater type orbitals. However, we could kind of solve this problem by using what's called a contracted GTO, which is a linear combination of Gaussians. For example, in these two figures here, I'm showing how a sum of 3 Gaussians almost produces a Slater type orbital. So this black line is a Slater type orbital, and this dashed line here is the sum of these 3 Gaussians. So the contracted GTOs can kind of solve that problem that I was mentioning. And it turns out that even using many Gaussian primitives, it's still faster than using a Slater type orbital. So this is an example of a contraction. For the hydrogen 1s orbital, it was found that these 4 Gaussian primitives minimizes the energy of the 1s hydrogen orbital. We can group these 4 Gaussian primitives into 2 contractions. So the first is just the first Gaussian primitive, and it's the diffuse Gaussian primitive. The second contraction is the next 3 Gaussian primitives, and these ones compose the compact Gaussians. So how were these contractions derived? Well, in the above example, the coefficients of the Gaussian primitives were derived which minimize the energy of the hydrogen atom. However, not all basis sets use this convention. Some, like the Popol basis set, use Hartree-Fock theory to derive their basis functions. Others are tailored for correlated calculations. For example, the Dunnings correlation consistent basis set uses I think it's CISD to derive their basis functions. Others are aimed for geometry, properties, etc. So if you're using a basis function, or sorry, a basis set that you're not familiar with, you're probably going to need to read the literature to find out how it was derived. However, for most average users, you're just going to be sticking with probably the Popol basis set or the Dunning basis set, which are often good enough. So why are the contractions done? Well, we already talked about that we need to approximate the STO, but the best result could be obtained if all of the coefficients in the expansion were allowed to vary. Well, it actually turns out that the computational effort, i.e. CPU time, for calculating these electronic structure theory calculations depends on the number of primitives, but all of the subsequent steps depend on the number of basis functions. Furthermore, the storage required for calculating these integrals is proportional to the number of basis functions, not the primitives. So essentially, we're using these contractions because it saves disk space and CPU time. So now let's talk about the different types of basis sets. The first one is a minimal basis set. So this has one basis function for each atomic orbital in the atom. The next is a double zeta basis set, which includes 2 basis functions for each atomic orbital. And we have triple zeta, which is 3, and etc. It goes QZ, 5Z, 6Z. Of course, having more basis functions for each atomic orbital allows the orbital to get bigger or smaller when other atoms approach it. And lastly, there's a thing called a split valence basis set. So this uses only one basis function for all the core orbitals and a larger basis set for the valence orbitals. So this is a little bit, so that more basis functions are assigned to the valence orbitals does not mean that the valence orbitals incorporate more primitives. So that might be a little bit of a tongue twister, but this is a good example. So in the 631G basis set, there's one basis function per core orbital and 2 basis functions per valence orbital, but the core orbitals are composed of 6 contractions, and the valence orbitals are composed of 4. So we need to differentiate orbitals and contractions. So these are some examples. So the hydrogen atom in the minimal basis set just has one s atomic orbital, so we have one basis function. The carbon atom in the minimal basis set has these 5 atomic orbitals, so it has 5 basis functions. The carbon atom in the double zeta basis set has 2 basis functions per atomic orbital, so it has a total of 10 basis functions. So how many basis functions for carbon atom using a split valence double zeta? Well, remember the split valence double zeta has a smaller basis set for the core than the valence. In this case, the core has 1 basis function, so that's 1. This has 2, so 2, 3, 4, 5, 6, 7, 8, 9. So that has 9 basis functions. Now I'm going to talk to you about shells. Gaussian primitives are grouped in shells corresponding to the same value of angular momentum. For example, 12s 9p 1d means that there's 12 primitives on the S shell, 9 primitives on the P shell, and 1 primitive on the D shell. To denote how just one more comment back here. These are the total number of primitives, and they've just been grouped together. Okay? To denote how the contractions were performed, the following notation is often used. So we go 12s 9p 1d to 5s 4p 1d. So these are the primitives, and now these are the contractions. So this means that.
Is that all right? Can I ask?
Yeah.
Yeah. So you're adding Gaussians together to get that orbital as a function of r to kind of get that shape by adding Gaussians together?
Yeah, and those are called contractions. So this means that 12s Gaussians were contracted to form 5s CGTOs, contracted Gaussian type orbitals.
Okay, and when you say different basis function, like the parameters can be different, but the functional form is changed when it's a different function?
I'm not sure if I follow. Can you repeat
what's the basis function?
The basis functions are those Gaussians.
Okay, okay.
Is everybody clear on that? Any other questions while I'm here?
So, like, what would an orbital made up of, how would you describe an orbital that's made up of two contracted basis functions mathematically?
I kind of showed what they look like over here. So this is a 1D slice. Of course, these are 3-dimensional. So here I was showing it a 2D slice. So that's what they look like. So you combine multiple Gaussian primitives to form your contracted GTO.
Well, yeah, but that's a single basis. That's a single basis.
Yes,
function, right?
yes. So then we use basis functions to form our orbitals.
So then what is?
So there's 3 layers to this. There's primitives, contractions, and then we use those contractions to form orbitals.
So then what is basis functionals being put together look like?
So
either just mathematically, like drawing out.
Yeah. I'll show you. It kind of looks something like. I guess I'll come over here.
Oh, so you just add everything?
So if this is 2 hydrogen atoms, it would look like that. So this is 1 GTO on that one. This is 1 GTO on that one, and they form an orbital in between them. A sigma orbital.
And the one on the screen, that looks like a Gaussian formula to me, kind of hidden. Is that
this one?
Corresponding to the plot?
Where?
Yeah, exactly.
Here? This is a weird nomenclature that they use. This means that 3 Gaussians have been put together to form 1 contracted GTO. It's a weird nomenclature. So STO3G means we've combined 3 Gaussian type orbitals.
Okay, so it is a Gaussian equation there.
Yes.
Yeah.
Yes. This is the Gaussian here, and we're just doing a linear combination. And then this black line is the STO. So and you can see the contracted GTO approximates the STO. Thanks for the questions. Okay. Okay, so we group our Gaussian primitives into shells, and this notation denotes how those primitives have been contracted together to form our contracted GTOs. So this notation means that 12s type Gaussians have been contracted to form 5 CGTOs. 9 p-type primitives were contracted to form 4 basis functions there, and 1 d primitive is a basis function by itself. So this might be a little confusing to you, but the statement 9 p-type primitives were contracted to 4 basis functions actually means that we formed 12 basis functions because each p-type primitive has 3 variants, x, y, and z. So we need to take into account degeneracy when counting these. Likewise, the d-type primitive here has 6 d-type So this is a notation that was on the previous page, which tells you how many contractions you're forming. However, this doesn't say how many primitives are in each contraction. All we know is we have 5 S-type contractions. We don't know how many primitives are in each contraction. The more elaborate notation explicitly lists the number of primitives in each contraction. So here, these are the S-type contractions. So we have a total of 5 S-type contractions, a total of 12 primitives, so 6, 9, 10, 11, 12, consisting, so the 5 contractions consist of 6, 3, 1, 1, and 1 primitives respectively. Does that make sense to everybody? Okay, I'm assuming that's good. It's a little confusing. That's like probably the hardest part of this whole presentation, though. So,
Makes sense to me.
No?
Yeah.
Okay, so these are our primitives. These are our contractions. So we have a total of 5 S contractions. We could write that. We could explicitly say how many primitives are in each contraction using this notation. So this says that the first contraction has 6 primitives, the second contraction has 3 primitives, etc. And these are all the S-type primitives. Likewise, the D-type contractions have, the first D-type contraction has 4 primitives, the second D-type contraction has 3 primitives, and 1 and 1. Does that make a little bit more sense now?
So is that notation just saying that you're not spreading the primitives around evenly?
Yes, we're not spreading them around evenly, exactly. So one of the contractions has 6, the next has 3, etc. So this notation just explicitly states how many primitives are in each contraction. So by counting the number of them, we could say how many contractions we have and how many primitives are in each contraction. This is only important if you want to count basis functions. So if you don't understand that, that's right now, that's fine. But if you ever need to count basis functions, this is how you do it. So now I'm going to talk to you about Popol basis sets. This is a very popular basis set used by a lot of people. The Popol basis set is a split valence basis set. So that means that there is more orbitals, so more basis functions on the valence orbitals than the core orbitals. In the Popol basis set, the basis set structure is defined by row in the periodic table, not by atom. So before, when I was talking about basis set types, I was saying for hydrogen, this is the basis set. For carbon, this is the basis set. Well, the Popol basis set just says all of the atoms in the second row have the same basis set, etc. So symbols like Nijg or Nijkg encode the split valence. So N is the number of primitives on the inner shell. Ij or Ijk is the number of primitives for the contractions in the valence shell. So the Ij notation means it's a double zeta quality, and Ijk means it's a triple zeta quality. So if you want to improve your basis set, just and you're working with 631G, just go up to 6311G, and that will help improve it a little bit. So 631G means that it's a split double zeta. It has 6 primitives on the inner and 3 + 1 primitives on the valence. And the valence is composed of 2 basis functions for each orbital.
So does each basis function on the valence, for the valence orbitals, do they each have 3 + 1 primitives?
No, the first one has 3 and the second one has 1.
Oh, okay.
So each,
Well, because this is a split valence one, so like so all the like core ones are gonna, you said, are going to be represented by a single basis function with a lot of primitives, and then the other ones are going to be represented by 2 basis functions with less primitives, one with 3, one with 1.
yeah, so the valence orbitals are composed of 2 basis functions each, 1 with 3, 1 with 1. The core are represented by 1 basis function with 6 primitives. If you remember earlier, I said that that more basis functions are used for the valence than the core does not mean more primitives are used for the valence. And you can see that here. The core has 6 primitives, whereas the valence has 4. But now the valence is composed of 2 basis functions each. So the basis set structure is also encoded. So for example, for 631G, the first row is a contraction of 4 S-type primitives to 2 S contractions. This could also be written in this notation, which is the more elaborate notation I showed you, which says that the first S-type contraction is composed of 3 primitives. The second S-type contraction is composed of 1 primitive. For the second row, it's this contraction. We go from 10S to 3S, 4P to 2P. And in this notation, it says that how many primitives are in each contraction. So now let's talk about polarization. The Popol basis set can also be augmented with D-type polarization for functions on D-type polarization functions on heavy atoms, which looks like a star. Sometimes it's also written as a parentheses D. And with P functions on hydrogen, which is a double star, or in parentheses PD. So that would look just like this, going from 631G to 631G star. This corresponds, again, to adding D-type contractions on carbon on the heavy atoms. So this can be represented in this notation. So these are our S contractions. These are our P contractions. And we're adding that D-type contraction there. It goes S, P, D. Remember that adding P-type contractions actually adds 3 basis functions per orbital. Sorry, 3 basis functions per orbital. Sorry, I mean 3 basis. I don't mean 3 basis. I think I mean primitives. And adding, oh no, I do mean, yeah, I do. Sorry. 3 basis functions per orbital, and D-type adds 6 basis functions per orbital. So when do we want to include polarization? So you want to include polarization basically in all situations that we're working with, because it's important for chemical bonding, and most of us are working with chemical bonding. And if you're ever working with a hypervalent atom, such as sulfur, you definitely want to include polarization. I include hydrogen. I include the double star when I'm working with hydrogen bonding because I want extra polarization on my hydrogen atoms. You also want to include polarization in correlated calculations such as CISD, CCSD. However, adding polarization is expensive because you're adding a bunch of basis functions, which can translate to hundreds or thousands of extra basis functions, depending on the size of your system. We could also add diffuse functions. So diffuse functions are S and P type orbitals, or sorry, basis functions which have a very small exponent, so they decay very slowly. They're very diffuse. That's why they're called diffuse. Diffuse functions are necessary for the correct description of anions and weak bonds, such as a hydrogen bond. These are actually quite economical to use, so I would recommend these. You're only adding a couple of basis functions, and they're absolutely necessary for anions, and they help out with weak bonds as well. For the Popol basis set, the following notation is used. You add a little plus when you're adding one diffuse S and P type, and you add 2 pluses when you're adding a diffuse S and P type to the heavy atoms, and 1 diffuse S type to the hydrogens. So this notation means you're adding extra diffuse functions to hydrogen. So if you're ever wondering what these basis functions look like, or if your research takes you down that route, you might end up looking at a table something like this. This table basically explains all of the exponents and coefficients of the Gaussian type orbitals. So tables like these can be found on this website, and again, it just gives the exponents for the Gaussians and the coefficients out in front. So this notation is a little weird too. It's called SP because if you notice, this row here, or this column here, are the S. Sorry, this column here is the S, and this column here is the P. The S and P here are sharing the same exponent, so the term SP is used. You won't have to worry about that unless for some reason you need to look up the basis set though. All right, another popular basis set that people use is the Dunnings correlation consistent basis set. If you recall at the beginning of this talk, I said that the different basis sets are formulated differently. For example, the Popol basis set uses Hartree-Fock. Well, the Dunning basis set uses CISD calculations to determine the coefficients and exponents of the Gaussians. So the notation that they use in these basis sets is CCPVX, which is just a variable here, and Z. So X could be D, T, Q, and 5. So if it's D, that means it's double zeta. If it's T, that means it's triple zeta. If it's Q, that means it's, what is Q? Quad zeta, I don't know. Sorry, and then 5 zeta. So functions are added in shells, and yeah, just kind of like the Popol basis set, but a little bit differently. So some more general comments. The bigger the basis set, is that always true? Well, usually, but you need to balance the level of theory with the basis set. You can't just use a really big basis set and expect to get the perfect answer. It's kind of like a you have to balance. You have to use a high level theory and a good basis set. Of course, that's not always possible, but definitely stick away from this basis set, the STO 3G. It's too small. And like I mentioned, it's hard to afford more than polarized double zeta because polarization just adds so many extra basis functions. And anions must have diffuse functions. I didn't know this, but it's very important to do that. And I use double star in hydrogen bonding, and I'm going to start using these diffuse functions because they're actually quite economical to use and they help out. So if you're working with wave function based methods, the convergence of these results with respect to basis set are pretty slow. And if you want to know more, you could look up these papers by Helga Kerr and Dunning. However, many of you probably are using DFT. DFT is actually less dependent on basis set than wave function based methods. So there's some good papers by Angela Wilson at MSU on that if you want to learn more. And if you actually want to look up what types of, what the basis set is, you could go to this website and it'll give you all the information. I'll provide that table. It'll tell you the contraction. And of course, I couldn't mention all the important basis sets. Others are out there, but I try to cover the 2 most popular ones. And I provided this self-test here at the end if you guys want to do it. I don't want to go through it by myself unless you guys want me to. But in this example, we could count the number of basis functions and primitives in water. So if you guys want to go through that, we can. Otherwise, I'm just leave it at that. Any questions? Here.
Can we go to the shells and contractions, please? Oh, actually, that's the one. My question was, why were there fewer CGTOs as you went from the SP to the D? Yeah.
So that's because the core orbitals are usually 1s. And so that core orbital is that one right there. So it has more than that one. Because we don't have a p-type core orbital, at least for carbon. So here we're saying that one of the basis functions is the core orbital, it's for the core orbitals, and it's composed of 6 contractions. So, Michael.
Is that because for the core orbitals you need to like
Yes. Yeah. So for the core, I didn't mention this, but it's a great question. So the core orbitals, we use more primitives for the core orbitals than the valence orbitals because we want to get that nice cusp shape that we see in hydrogen here. Whereas the valence, we just need more basis functions, more or less.
So what is the difference between having more primitives versus having, or well, what's the difference between having fewer basis functions, each with more primitives, versus having more basis functions, each with less primitives? Like how is that different?
So I mentioned before that they use contractions because you end up saving disk space and CPU time. So contracting the primitives into these CGTOs saves storage and computational effort.
So it's cheaper to use more primitives.
It's cheaper to use more primitives than more basis functions.
So then why are using more basis functions more accurate?
Just because you have more flexibility in the orbital. Yeah, I mean, I think that this is actually an interesting question because computers are always evolving. So, I mean, I'd have to look at the literature to see exactly how this works out. I mean, maybe we should start questioning whether we should just be using more primitives or just not using contractions at all. I don't research this, so I have no idea.
Oh, okay.
But, I mean, if you probably look up the primary literature, you could actually see the speed increase or at least the memory storage problem. So I guess since we have some time, oh wait, question.
So basis sets are not part of DFT, they're separate, you're saying?
Yeah, basis sets are, they're used by all different types of electronic structure theory methods.
They come in DFT, but they're not like necessitated by DFT theory.
Okay,
I guess we'll look into that a bit
because
more.
the DFT is the functional of that orbital that gives energy.
Yeah. Functional best. Which is still not the order. Anyway, I'll keep that in mind during my talk. I'll look at this again.
So I know, so this, let's go, I guess we could go over this example since I have some time. So you might want to know, for example, how many basis functions are on your molecule, or how many basis functions you're using in your electronic structure theory calculation. For example, I know Eric here is working on some machine learning, so he needs to know what the orbitals are. I've needed to count them before because I wanted to look at specific orbitals. So in order to count the number of basis functions, for example, on water, using this basis set, we could write out the notation for the basis set. So if you recall, this is the notation that describes how many primitives are in each contraction. So the red ones here are the S-type contractions, the blue ones are the P-type contractions, and the green ones are the D-type contractions. So these are because oxygen is in the second row, these are the basis functions for oxygen. However, hydrogen is in the first row, so it has a smaller set because we're working with the split double zeta basis set. So if we want to count how many basis functions we have one oxygen. There is 3 S-type contractions, 1, 2, and 3, and those have a degeneracy of 1. There's 2 P-type contractions, but remember each P-type contraction consists of PX, PY, and PZ, so it has a degeneracy of 3. There's 1 D-type contraction, and it has a degeneracy of 6. There's 2 hydrogens. There's 2 S-type contractions. Those have a degeneracy of 1. There's 1 P-type contraction. Those have a degeneracy of 3. So if we count all those up, we get a total of 25 basis functions. Is that clear to everybody?
Why is the D6?
Yeah, so we're supposed to have 5, but mathematically it works out that we have 6. I can't remember exactly why, but so this is a little weird. So some basis sets remove that extra one, but some don't.
Isn't it a cartesian versus?
Yes, spherical, I think, or something.
Spherical coordinates.
Yeah.
Okay. So one of them's redundant, essentially?
Yeah. So some basis sets remove that extra one, but some don't. So now we can count how many primitives we have. So for oxygen, we have a total of 6, 9, 10. Oh, sorry. Yeah, 10 S-type primitives, 4 P-type primitives with a degeneracy of 3, and 1 D-type primitive with a degeneracy of 6. We have 2 hydrogens, 4 S-type, and 1 P-type with a degeneracy of 3. So if we add all this together, we have a total number of 42 primitives. All right, last thing. What's up?
So why isn't S of hydrogen, why isn't that 61?
Because we're working with the Popol split valence. So split valence, we have less.
Hydrogen doesn't have a core orbital. It's just 1s. So we give it a 3-1 valence.
Okay, so if you want more information, I got most of my information from this website. It's ccl.net. Just search basis set. It goes over pretty much exactly what I went over. Another good reference is David Sherrill at Georgia Tech's basis set. He has a PDF online. He's a really excellent educator. And also, I got some information from this book by Atkins. It has a nice section on basis sets as well as DFT if you're interested. All right, thank you guys again.
Thank you.